going to study about non-isolated systems which involve friction, and let's try to calculate the work done in such systems. So first of all, let us revise what is a non-isolated system. Non-isolated system is one in which there is a transfer of energy, and that transfer or change of energy takes place due to work done by some external force, or by heat, or by transfer due to electromagnetic waves, electrical transfer, and so on. Okay. So in this particular situation, there is no other transfer. There is no electromagnetic rays, there is no mechanical waves, or there is no heat transfer. So all these, they are zero. The only way of transfer of energy is by work done. So the change in energy is only due to the work done on the system. Now work done means that work done due to external force, or all the forces that are acting on the system. Okay, so we say that let's not confine it to only external forces. Let us say that it is the work done due to all the forces and that are acting on the system. Okay, so this is what we are going to deal with. So it means that we are going to apply some force and find out what is the change in energy and what is the work done. So now let us say that you have a system in which there is an object. Let us say the mass of the object is m, and suppose it is kept on some table, and this table is not smooth, it is rough. So because of its roughness, it will have some frictional force acting. Due to this table, there will be frictional force on this mass m. So frictional force is a type of very complicated force, and many scientists, they have tried to explain it, that how a frictional force works on a system. So one of the theories which explains the frictional force is, they say that it is the interlocking of the interface. So interface means we're just talking about this part of the mass and the table interface. Okay, so this interface is what is this. So it means that this is m here and this is table here. So we're just talking about the interface of the two objects where they are sticking together, so that we can understand how friction works. So one of the theories is that the surfaces are rough, so rough mass, rough table surface, and they interlock like this. And the other theory, one of the other theories is that they don't interlock like this, but they act as if they are welded, their points are welded to each other. So in this theory, they say that the mass and the table, this interface between the two is such that their points, the rough points, they are welded to the points. So one is mass and one is the table. So mass and table, their surfaces, they are welded to each other for a moment when the object is kept on the surface of the table. So this actually, it just shows the interface of mass and the table. And now let us say that we apply some external force on this mass, and when we apply some external force, okay, so we are applying some external force on this table, so it means that the mass will move in this manner, but there is friction which is acting in the opposite direction. So it means that the interlocked region will also be shifted. So if this is the interlocked region, so if we are applying a force on the mass m, so this is m and this is table, and we are applying a force on the mass m. So mass will move in this direction, but table will still try to hold it because of this welding points. Okay, so it will behave something like this, that the mass will move in this direction due to the force applied, and the table is not moving, so table is staying at the same point as it was. Okay, so and these welded points, they are still trying to make a contact with the mass. Okay, and this entire distance is d upon 2 and d upon 2, so the total distance, let us say, is d. Now so you know that if force is acting in this direction, then force of friction will be in the other direction, and if the object is moving, then the force of friction, if the object is moving, then the force of friction will be kinetic friction. Okay, so external force is in this direction and kinetic friction is in the opposite direction. So if we have to draw it here, it means that external force is acting in this direction and the force of friction, the kinetic friction, will be in the opposite direction. Now, a frictional force is actually not at a particular point. It is on all of the surface. So if there is an object kept on the table, then force of friction will act on each point. It is not confined to a particular point. So that is why this is actually one of the points we are talking about. So let us say that this is just this part of the table. So we will have many such points on which force of friction will be acting. So we cannot add it directly to the work done because it does not act at one point. So you know, at this situation we have many forces acting. Let us say that there is a gravitational force in the downward direction, there will be normal force in the upward direction. So what we are going to do is we are going to find out the work done for this kind of situation. So let us say that we are going to find out the work done by all the forces. This is the work done by all the forces which are acting on this object except for frictional force. So if you have to find out the work done, and this work done is being found by, and this work done is done by all the forces but except for friction, then it will be equal to, let's start from the basic definition of work done. You know, work done is force into displacement, and it is also written by total force into displacement vector. So this will be the work done by all the forces, but here this forces, this will be this forces, because we are saying that all forces except friction. So these forces are all forces. This summation means, this means all forces except frictional force. Okay, because the object is moving, so we say it is kinetic friction. So we add a subscript Fk. Okay, so now what we do is, let us say that towards this side I add some extra term. Okay, and let us say it is kinetic friction vector dot dr vector. So first we have this situation that we are saying that work done by all the forces except friction will be equal to integral of all the forces except friction dot displacement. Now what we are doing, we are adding a term towards this side and we are adding a term towards this side. So let's add the same term towards the other side also, so it will not change anything. Okay, so in this equation we've added this term on both the sides, and now let us see what happens. So when we are saying that all forces except friction, and then we say frictional force, it means all forces. So let me just explain it to you what it means. Now let us say that we are saying that we have summation F, total number of forces, which is F1, F2 plus F3. Okay, now if I say that let me add total forces except F3 will be F1 plus F2. Okay, Now what do I do is all forces except F3 plus F3. What will it mean? It will mean F1 plus F2 plus F3. So it means it is a sum of all the forces that are applied. So if we apply the same logic here, so we are saying all forces except friction plus friction, then this equation would turn out to be, let me take another paper. Okay. So then this side of the equation will turn out to be integral of all the forces dot dr vector. Why? Okay, let me just write it in two steps maybe. So we can take these two forces together, and so it will turn out to be all except friction plus friction dot displacement vector. So all except friction plus friction will mean all the forces. Dr vector. Okay. So now we have this equation. So if we have many forces, there might be many forces, but the acceleration will be one. So by Newton's second law, we can say that all forces will give rise to one acceleration. So it will be ma vector dot dr vector. And what is a vector? It will be derivative of dv vector. So it will be m dv upon dt dot dr vector. Let us multiply and divide it with dt. So we divide with dt, we multiply with dt. So this becomes integral of m dv, and dr upon dt is nothing but v. So it will be m dv vector dot v vector into dt. So now we are going to find out a relation, a simplified way of writing this term. Okay. So in order to find this, let us say that this is equal to star. Okay. So we are going to find this first, and we are also going to find this term also. But let's focus on finding this one first. So in order to find star, let us say that we are taking a derivative of v vector dot v vector. Okay. So what will it be? Now if we take a derivative of any vector, let us say a vector dot c vector, what will it be? It will be dA vector upon dt dot c vector plus a vector dot dc vector upon dt. So on the same lines we can write for this, it will be v vector dot dv vector upon dt. Okay, let's take a derivative first, although it doesn't change anything, plus v vector dot dv vector upon dt. Okay, this I've just taken to give you an example that how a dot product of vectors they behave. Okay, so by using this equation we can write this equation. Okay, so then it turns out to be that, okay, so before I write anything, let me just tell you a few more things. Now this is v vector dot v vector, so it is just like a vector product. So if you have two vectors and it is a vector dot b vector, we simply write a magnitude, b magnitude to sine of theta. Okay. In the similar manner, v vector dot v vector will be v magnitude, V magnitude, and cosine of, now they're same, so cosine of 0. Cosine of 0 will mean 1. V magnitude means V, so it will be V square. So V vector dot V vector will be equal to V square. Okay. Similarly, now we can add these two, but how and why? This is because A vector dot B vector is equal to B vector dot A vector. That is why we can say that dV vector, so it means that dV vector upon dt dot V vector should be equal to V vector dot dV vector upon dt. So you can use this also. So use both of them in this equation, and what we'll get is d upon dt of V squared must be equal to twice of dV vector upon dt dot V vector. Okay, so it means, as we have demarcated here, that it is this term we were trying to find out. So it means that star will be dV vector upon dt dot V vector will be equal to 1 upon 2 of dV square upon dt. Okay. So this whole calculation we have done just to find this term in this equation. So now let's put this value in this equation. So we are just going to replace this term by this term. Okay, so it means that now this equation would be integral of m. Now we know that this is equal to 1 upon 2 of d upon dt of V square into, we just replace this term, which is 1 upon 2 of dV square upon dt, which we've just found here. Okay, this one. So we've just replaced this term by this term. Okay, so this is what we get from this side of the equation. So we can cancel dt and dt, so it will be 1 upon 2. M is a constant and the only variable will be dV square. Now we're going to integrate this from Vi to Vf. Let us say it is from Vi to Vf. So it is a very easy integration, but just in order to explain, maybe I can just give you a hint how to do it. V square is equal to U, so it will be 2V dV upon du will be equal to 1, or you can say that du will be equal to 2V dV. Okay, or simply from here you can write directly from here also, that du upon dV will be equal to 2V. Okay, so if we take an integral of dV square, then it will be integral of du. Okay, or we can say that it will be, maybe I'll write it here itself, so it will be integral of 2V dV. So Vi, and it is integrating from Vi to Vf, so 2 will cancel with 2, and what we are left with is m integral of V dV, and where V is changing from Vi to Vf, so it will be mv square upon 2 Vi to Vf, which means 1 upon 2 mvf squared minus 1 upon 2 mvi squared, which is nothing but kinetic energy, final kinetic energy minus initial kinetic energy, which means change in kinetic energy. So it means that work done by all the forces except for friction plus this term gives you the change in kinetic energy. Now let's try to figure out the second term in this equation. So if I have to write this equation here, it just means that work done by all forces except kinetic friction plus integral of kinetic friction vector dot dr vector. So this will be the equation now. Now we have got this term kinetic friction dot dr vector. Now let's try to find out this term. Now let us say that this term is given by this sign. So now let's try to find this. It will be given by integral of kinetic friction vector dot dr vector. Now when we are moving the mass, we see that the force is being applied in this direction, external force, and on this object the frictional force is acting opposite to the external force, and the displacement, so the object is moving in this direction, so dr vector will also be in this direction, and the object is moving by a distance of, total distance of d. This distance is d, as we have seen when we just started with this topic, that the object moves by a distance d. So it means that integral of total distance traveled by d by this object will be d. Okay. So if we have to find out this term, it will be kinetic friction dot product. So magnitude dr magnitude into cosine of theta. Now the angle between displacement and kinetic friction, they're opposite to each other, so the angle between them will be 180 degrees, so it will be 180. So what we get from here is minus integral of kinetic friction dr, because cosine of 180 will be minus 1. So kinetic friction, the variable here is r, so let's take it outside, and so it means integral of dr means total displacement, and as we have said that the total displacement is d, so it will be minus fk into d. So this term here, it turns out to be equal to minus fk. So if I again write this equation, it will be something like this. So work done by all forces except kinetic friction plus, now this term is actually equal to minus kinetic friction into total displacement. So let us use it. So we'll get a negative here, so it will be k d would be equal to delta k. So this is what we get from all this mathematics. This is the equation we get. Okay. So in our case, the only force which will create displacement will be the external force, because when there is an object and there is some force acting on it, which is external force, and there is frictional force, and this object moves a distance of, total distance of d, then in this situation, if it means that the work done is only done by external force, because gravitational force and the work done by both of them will be equal to 0. So work done by gravitational force and work done by normal force will be equal to 0. So it means that work done by all forces except kinetic friction will be Gn plus work done by external force. So if they both are 0, then the work done will only be by the external force. Now if the work done is only by external force, if suppose external force is equal to 0, then it will mean that the work done by external force will be 0, because work done is force into displacement. So if force is 0, external force is 0, work done by external force will be equal to 0. So this is 0, this will automatically be equal to 0. So then this equation, in this equation it means that, okay, before going into this, I should have told you something related to this equation. Now, in this equation, you see that here we have change in kinetic energy, because there is no change in potential energy. The object is moving at the same height from one point to the other, but the height is not changing. But if in some situations, if suppose in some situations height is changing and delta U is not equal to 0, then this equation will be work done by external force minus D will be equal to delta K plus delta U, if delta U is not equal to 0. So, and this we know that all except frictional force is actually equal to external only, work done by external force. So this will be our equation, final equation. Okay. If there is a change in height, then delta U will not be equal to 0. So let us now consider this situation. So if external is 0, this will be equal to 0. So we can say that FKT will be equal to delta K plus delta U, or delta K plus delta U plus will be equal to 0. Okay. Now, in this equation, so we got this equation where delta K plus delta U is equal to kinetic friction into displacement, and we are saying that external force is 0. Now if we remember, then in an isolated system, external force is equal to 0, and if external force is equal to 0, then the total change in energy will be equal to 0, because we don't have any other transfer, we just had work. And if work is also 0, then it will behave as an isolated system. Delta E will be equal to 0. Now, when we say this E, this actually means the total energy of the system is change in total energy of the system is equal to 0. But what is the total energy of the system? Now, let us say that if there is some object and it is moving with some velocity v, then it will have only kinetic energy. Okay. But if suppose that there is an object and it is moving from height to another height, h is changing, then it will have kinetic energy plus potential energy. Now, let us say in this situation it is ice, so there is no friction. In the third case, suppose that there is an object and this is not ice now, this is a rough surface. And this object is moving downwards and it reaches somewhere here. And it has velocity. So if it has velocity, it means it will have kinetic energy. And because it is at some height h maybe, so it will also have potential energy because of this change in height. So now, if the total energy of the system, it means will be kinetic energy plus potential energy. But now in this case it is a rough surface, so it means there will be friction acting opposite to motion. And due to this friction, there will be some heat generated, and the atoms of this object, it will start moving with higher energy in different directions. So it means that its internal energy, which is the energy of the atoms of an object, it will also change. Okay, so it means it will have an additional term which is called the internal energy of the system. So the total energy of the system is kinetic, potential due to height, and internal due to friction. It has changed due to friction. Otherwise it will stay constant. Like in this case, the internal energy will be constant, so there will be no internal energy, but there will be no change in internal energy. So this is the total E we're talking about in this equation. So total E, change in E will be delta K plus delta U plus change in the internal energy. So when we are saying that the system is isolated, then delta E must equal to 0. So it means that this equation, delta K plus delta U plus delta internal is equal to 0. We get this equation. Okay. And if we compare 1 and if we compare 2, what we can conclude is that change in internal energy must equal to this term. So change in internal energy must equal to kinetic friction into D. So it means that friction will increase or it will change the internal energy of a system. So this is an important equation. So we have to remember all these equations which we have studied, which is this equation, that change in external force, work done by external force minus kinetic friction into displacement is equal to delta K plus delta U. We need to remember this. And the other one would be this equation, that delta K plus delta U plus this is equal to 0. And change in internal energy will be equal to kinetic friction into displacement.